Hi, my name is Marian Flint, and this is Lab 3 Circuits. So to begin, the purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, measure the actual values of conventional current and potential differences in the circuits, examine the behavior of ohmic resistors and capacitors, and the physics concepts that are important is the loop rule, the node rule, and Ohm's law. So as you can see, the loop rule is the sum of potential differences in a loop all equals to 0. And current entering a node will equal the current leaving a node. That's a node rule. And then Ohm's law just says that the difference in potential is equal to the current times the resistance. So in part 1, the predicting current I calculated with delta V equals IR. So as you can see, I did 3 times 147, and I got 0.0204 amperes. And then my actual current from the app was 0.02 amperes. And reversed, it was also 0.02. So as you can see, it's pretty close. And then voltmeter reading, I got 3 volts coming out of the battery and 0 volts from the open wire. So here is the difference in voltage around the circuit. So you can see the different labels for node 1 and node 2. So based on where it's like going through, which ones, you can see the delta V. So for B and A, it was 3 volts, and then 0 volts for B and C. And as you can see, the sum is always 0. So it does follow the loop rule of wherever it's going through. And then delta V around the circuit, we can also see that just like shown in a different way here. So we've got voltmeter reading the delta V around the different parts of the circuit. So here's my resistance calculations. So for the different resistors, I got 47.95 for the 47 ohm, and then for the 100, it was 102.5. The R wire was 0, the R ammeter was 0, and this all follows Ohm's law. So the circuit, we have the charged 10 ohm bulb, it was 5.9 seconds. Discharge was 6.8 seconds. The charged 20 ohm bulb was 8.8, and the discharge 20 ohm bulb was 8.9. So as you can see, there's not much difference between those. Next, we have the capacitor voltage, which I just modeled here. On the y-axis, we have the natural log of V over V initial, so that's like our delta V, and then time on the axis. So we can see as time increases, that value decreases. So our slope was -1 over RC, and we got that RC was 5.98. And I wrote that this is comparable to capacitance 0.2 times 30 ohms. So, okay, reflection. If we were doing this in real life and we're using an actual ammeter instead of an ideal simulated ammeter, this would affect the resistance. So in real life, there would just be a lot more resistance because there is resistance from wires and things that you're hooking up, but in this ideal ammeter, there's no resistance because it's modeled after like a perfect system, which is not possible to achieve in real life. And then if you used a battery to charge a real capacitor with no resistor, then the capacitor would charge instantly. So in real life, resistance slows down the charging process, but if we had an ideal ammeter in real life and a capacitor with no resistor, then the capacitor would charge instantaneously, which is obviously different from real life where we do have to experience that resistance, slowing down the process. Thank you.